addition of scalar is a bit easier. When you add 2 kg of rice with 3 kg of rice, you will get 5 kg of rice. When you pour 2 kg of rice with 3 kg of wheat, you will get a mixture of 5 kilo comprising wheat and rice. If you add salt, sugar, masala to some quantity of rice and some vegetables also, you will get a mixture of a nice mixture of curries. Very palatable dishes you can prepare by pouring different quantities of different foodstuffs. So the preparation of entire things whatever we are observing in this universe is basically due to a proper admixture of different scalar quantities. And that's very, very fascinating. That's very fascinating. So the entire universe, observable universe, what you can see is really very attractive, very extremely interesting due to the mixture of the scalars. You can take different metals in different proportions. You can put it under a very high temperature, you will get alloys of different types of alloys you can get. So it's very easy to understand the mixture of scalars, the addition of scalars, addition of mass, addition of volume, addition of length. But in this class we will talk about the addition of vectors. A vector has an additional thing that is called direction. When you are adding one vector with the other vector, you are not only adding the magnitude of each vector, but also you are taking the direction of these vectors into account. So first of all, what is the basic meaning of addition of vectors? As I told you, when you pull my hand in this direction with a force of 5 Newton, and when you are pulling my other hand in opposite direction with a force of 5 Newton, that means you are adding this force with this force. And as a net, I don't move anywhere. So addition of these two forces will be equal to 0. So one proof is enough. One statement is enough to disprove a particular thing. And to prove that particular thing, we need countless arguments. So it goes without saying that the addition of vectors obeys different set of principles. In other words, we can say that the addition of vector is known as vector algebra, that is different from scalar algebra. For instance, if two scalars are added, a plus b square is equal to a square plus b square plus 2ab. We know that. But for the addition of two vectors, we cannot write a square plus b square plus 2ab is equal to a plus b whole square. We will be getting some direction factor. The angle between these two vectors will come into play when we will derive the equations. So what is the basic meaning of addition of vectors? How a vector is added with other vector? When we are adding the magnitude, how we can add that magnitude? And the second thing is coming, how we are adding the direction. Adding the magnitude of two quantities, it is a bit easier to understand. 1 plus 2 is equal to 3 always. But 1 meter plus 2 meter displacement may not be equal to 3 meter displacement. 1 meter per second plus 2 meter per second velocity may not be equal to 3 meter per second. 5 Newton force plus 5 Newton force is not equal to 10 Newton force always. So when you are applying certain force, 3-4 forces suppose on a particular object, you are pushing in this direction, other guy is pushing in that direction, other guy is pulling in other direction, other guy is pulling in some other direction. That means each guy is putting the force, adding the force on that particular object. And when you withdraw the forces, that is called subtraction of forces. But for the addition of vectors, we need to take the example of displacement, because displacement is a very basic type of vector. Displacement is a vector which is used as a scale, a prototype to understand the other vectors. So we'll talk about the displacement now. As I discussed, the recipe of addition of scalar is really interesting, but the recipe of addition of vector is more interesting because it has an extra thing, that is direction. For this purpose, we have chosen the simplest vector, that is displacement. What is displacement? When you move from one place to the other place, one location to the other location, you have to change your position. When you change the position, you are bound to move. At what rate you are changing the position? That is known as velocity. We'll talk about the velocity very vividly in kinematics. Suppose you move from New Delhi to London. You may choose many different routes. You can go via Colombo. You can go via Dubai, but the destination is London. You can choose different paths, but you have a single destination. So when somebody will ask you where you are moving, the answer is, I am moving to London. Then a question can be raised, where London is located. So it is quite simple, quite basic. It's a matter of common sense to answer that London is having such and such distance from New Delhi, and it is located in such and such direction. This means you are mentioning the position of the London with respect to New Delhi. And that is what we call displacement vector. When you move from one position to the other position, the initial position is the starting position, the final position is the destination. The position of the final point, the position of the destination with respect to the initial or the starting position, a starting location or the starting point is known as displacement. It's characterized by vector quantity. Because position vector is a vector quantity, position of an object is characterized by vector quantity. I talked about this particular position vector in my first video. So the position of an object, position of a particular place, a particular location with respect to some other location is a vector quantity. So that is what we call displacement. Now I will take the example of displacement of the tip of the marker on the whiteboard. If you start from the point, say A, you follow any path and you reach this point B. So what is the starting point? This is the starting point. This is the starting point. And B is the final point. Starting point can also be called initial point. Starting point or initial point. This is the destination. And this is the path. Path followed by the object. Path followed by, what is the object here? The tip of the pen is the object. This follows this path, but it is reaching this point. I can follow any other path like this, and I can reach the destination again. This path number 1, this is path number 2. Many different paths, countless different paths I can follow, but always I have some destination, and that is always a constant quantity for all types of paths. Which is a constant quantity? Fixed quantity for different paths. That is what we call displacement, given by the letter S. It's called displacement vector. It is a vector quantity. Its magnitude is the length of the minimum distance between the final and initial point, final and initial position, and the direction is given by the tip of the arrow points from the initial point or the starting point to the final point or the destination. So you can note it that displacement, it is defined as a vector quantity when a point or a particle moves from one position to the other, which is the first position A to the other position. What is the other position? Or the final position? B. It is defined as a vector quantity denoted by the symbol S. When a particle moves from one position A to the other position B. The magnitude of the displacement is equal to the straight line distance or the shortest distance or the minimum distance between these 2 points. And it points in which direction? It points from the starting point to the starting position to the final position. And it points from A to B, initial to final position. This is the magnitude and this is the direction. When we have the magnitude along with the directional nature, we can call it a vector quantity. This is the first fundamental vector after position. Of course, displacement is nothing but the position vector of the final point with respect to the initial point. We can note in this way. Displacement vector is defined as the position of the final point with respect to the initial point. Position vector of B relative to A. Using the displacement vector, which is the simplest vector, it is the most physically realized. You can understand it because when the tip is actually moving from A to B, the shortest distance between A and B directed from A to B is defined as displacement. Using this very powerful, most powerful vector, which will serve as a prototype, a scale to understand the other vector, we will press it to explain you what exactly the addition of displacement is. Well, we will take the example of the displacement vector to understand what the addition of vector is. Let us move the tip of the marker from starting point, that is A, to the destination or the final point B. The tip is actually moving. For the sake of simplicity, let us move the tip along a straight line. You can move from A to B in any way you like, any path you like, but for the sake of simplicity, I have chosen the straight path. And we can move the point B via another point, that will be P. When you are moving from A to P along a straight line, this is the displacement you are undergoing. You are undergoing this displacement S1 while you are moving from A to P. Again, you move from P to B in a straight line. While you are moving, you are undergoing another displacement. That is the displacement S2. This displacement is S2 when you are moving from P to B. But what you are getting, you are moving along this path, straight path, undergoing a displacement S1, then you are undergoing another displacement S2 while you are moving in a straight path. Of course, you need not move in a straight path, but for the sake of simplicity, I have taken a straight path. So after two successive displacements, what you are getting? You are getting the destination. This is the resultant. What is the result of these two displacements? The result of these two displacements is the displacement S, which is pointing from A to B. This is the resultant displacement. This is called resultant displacement S, because this is the resulting point, the destination, the result of these two displacements. So we can write After undergoing two successive displacements, S1 and S2, finally we attain the position B, which means finally the tip of the pen attains the position B. From which point we have started? After undergoing two successive displacements S1 and S2, from A, finally the tip attains the position B. Since B is the destination or resulting position, we can write the resultant displacement S as a summation of these two displacements. Summation means addition, or resultant, addition, summation, net. All these terms are equivalent. So the resultant displacement is given by this equation. S1 plus S2 is equal to S. So the addition of two vectors, two displacements, is equal to the resulting displacement. This is the total physical effect, because physically, really, you are moving the tip from A to P, undergoing a displacement S1, again from P to B, undergoing displacement S2. This is the final resulting point. This is the starting point. This is the final point. This is the initial point. This is the destination, and this is the first point. This is the second point. So this is the resultant displacement. The shortest distance between A and B, directed from A to B, directed from the initial to final point or final position. So this particular effect gives us the idea what a vector addition is. You can see here that we have conducted a real experiment. It is not an abstract thing. It is not just a construction. This is a real experiment that the tip is undergoing the displacement S1, then it undergoes the displacement S2, and as a result, it attains this point P. AB is the displacement. This is net displacement or resultant displacement or vector sum of these two displacements. So, after undergoing two successive displacements, S1 and S2, this is S1, this is S2, from A, finally, the tip attains the position B. Since B is the destination or resulting position, the resultant displacement can be written as sum of these two displacements. So we can write this S as resultant or sum or addition or net. All these terms are equivalent. So the net displacement or resultant displacement is equal to vector sum of these two displacements. So this is the idea. But always this may not be the case. Sometimes you may think that S is equal to S1 plus S2. This is a confusion. What is the confusion? We write S is equal to S1 plus S2. This is just simply the magnitude of the resulting factor is equal to magnitude of the first displacement plus the magnitude of the second displacement. If you write this is a wrong statement. This is correct. This is the vector sum of these two displacements is equal to the net displacement or resulting displacement. This is the scalar sum of these two displacements is equal to the net displacement's magnitude. This is a wrong thing. This may happen. It may be true in a specific case. When S1 is parallel to S2. When these two displacements are happening in some line, if it moves from A to P and P to B along the same line, then the resulting displacement can be written in this way. The magnitude of the resulting displacement is equal to the magnitude of the first displacement plus the magnitude of the second displacement. I can draw the diagram in this way. This is S1. This is A2, P, and this is S2, P2, B. Then the resulting displacement can be given by drawing an arrow from A in the direction of B. It will pass through P along a straight line or in a straight line. So we can just write S is equal to S1 plus S2. This is always correct, and this is also correct in this case when S1 and S2 are parallel or S1 and S2 are collinear. Well, this is a special case, but in general, these three factors S1, S2 and S, they form a triangle, and this triangle is called vector triangle because the triangle is formed by three vectors. Therefore, this is called a vector triangle. And this vector triangle, the sides AP and PB, they are S1 and S2 vectors. They are taken in a particular sense. If this is clockwise sense. If this is anti-clockwise sense, this will be clockwise sense. This is clockwise. This is anti-clockwise sense. In this triangle, if these two sides AP and PB taken in a particular order, that is anti-clockwise sense or anti-clockwise order, then the closing side, these two are the which side? Any two sides, AP and PB, they are taken in anti-clockwise sense or anti-clockwise order. If they represent two vectors S1 and S2, the closing side, this is the closing side of the triangle, AB is the closing side, taken in the reverse order. If it is anti-clockwise, then it is clockwise. Clockwise is the reverse of anti-clockwise. Taken in the reverse order will give you the resultant of these two vectors. This is the resultant displacement, S is equal to S1 plus S2. This is what we call triangle of vectors. So this is the triangle law of vector addition. Which states that if any triangle you are taking, you choose any two sides of a triangle taken in one sense. We have chosen the triangle is APB. We have chosen AP and PB are these two sides taken in anti-clockwise sense. If they represent these two vectors, two displacements S1 and S2, the closing side AP, taken in reverse order, clockwise order, must represent the resultant or the sum of these two vectors, two displacements. Therefore, you can write S is equal to S1 plus S2. I can note it down. Let me write the statement of triangle law of vector addition. If any two sides of a triangle, if any two sides of a triangle represent two vectors S1 and S2, say they in or taken in one sense, the sense is anti-clockwise sense, then the closing side, what is the closing side? AB, taken in the reverse order. What is the reverse order? These two sides are taken in anti-clockwise sense. So this closing side must be taken in the reverse order, means clockwise sense. Taken in the reverse order must represent the vector sum or resultant of these two vectors. So S is equal to S1 plus S2. This is the statement of triangle law of vectors. Let us reverse the vector, resultant vector S. Reverse the direction of this resultant vector S, keeping its magnitude same. It will be minus S now. We are just reversing its direction, it will be minus S. These two vectors are negative vectors that I have already discussed. Let this vector be another vector S3. Now we can write S1 plus S2, take S to the side, minus S vector is equal to 0. Or minus S, instead of minus S, I can write S3. S1 plus S2 plus S3 is equal to 0. This is another form of triangle law of vectors, which tells that if the sides of a triangle taken in one sense, we are taking the sides AB, PB and BA. In which sense? In anticlockwise sense. Then the sum of these three sides, when they represent these vectors S1, S2 and S3, must be equal to 0. So when the sides of any triangle taken in one sense represent three vectors S1, S2 and S3, the resultant of these three vectors will be equal to 0. This is another form of statement of triangle law of vectors. Let me write it now. So we have obtained two different equations, two different forms of triangle law of vector addition. This is very important statements. The first statement is that if any two sides of a triangle, this is the triangle APV, represent two vectors S1 and S2, AP represents S1, PB represents S2. Taken in one sense, what is that sense? APB, A, P, B. Which sense? A to P, P to B. Which sense? Anticlockwise sense, taken in one sense. Then the closing side of the triangle, what is the closing side? AB. Taken in which sense? AB is taken in opposite sense of anticlockwise, that is the clockwise sense. The closing side AB taken in the reverse order or reverse sense. The sense or order, both are same thing. Must represent the vector sum or the resultant or the net effect of S1 and S2. Resultant is of these two vectors, S1 and S2. S is equal to S1 and S2. So this is the equation, this is the statement of triangle law of vectors. And when you write S1 plus S2, take S to this side, bring all this lattice to left hand side, S1 plus S2, minus S equal to 0, it will be 0 vector. Minus S, what is minus S? This is the S vector, AB vector. Minus S means just direction is opposite, magnitude remains same. Minus S vector, let it be S3 vector. So instead of minus S, write S3, we will get S1 plus S2 plus S3 is equal to 0. Since these are all displacement vectors, this must be a vector quantity, that's 0 vector. This is another example of 0 vector when I discussed. The types of vector, there I talked about the 0 vector. This is the practical example of 0 vector. So how to get a zero vector? If any triangle you are taking in a particular sense, either you take anti-clockwise sense or you take clockwise sense. If you take anti-clockwise sense, it will be AP plus PB plus BA taken in one sense. What is that sense? Anti-clockwise. These three sides of this triangle are taken in anti-clockwise sense. You can take clockwise sense also. AP, A to P, then PB, P to B, then BA, B to A must be equal to zero vector. What is AP? AP stands for displacement 1 S1, PB stands for displacement 2 S2, and BA stands for displacement S3. That's equal to 0. That's what we obtained. So we can note that if the sides of a triangle taken in a particular sense of particular order represent the vectors S1, S2 and S3. Sum of these vectors will be a zero vector. You can see here the alternate statement. If the sides of a triangle taken in a particular sense or particular order represent the vectors S1, S2 and S3. We have taken the vectors in which sense, which order? Anti-clockwise order. Then the resultant of these three, or the net effect of these three vectors S1 plus S2 plus S3 will be equal to zero vector. Now the question arises, what is the meaning of zero vector here, physical meaning of zero vector? Well, this is the proper example I have given you to explain the significance of zero vector. Look, this is a real diagram, a real life diagram of displacement. You are undergoing a displacement S1. I mean, you are getting an arrow. The length of the arrow is equal to the length of the displacement. But when you move from a particular place A to any place B, in any other place, suppose in the ground if you move for 40 meters you move, then you cannot say that 40 meter is equal to AP, because AP may be 40 centimeter. So you have to take a scale and reduce that 40 meter displacement to the 40 centimeter arrow. But this arrow itself is the displacement because the tip of the pen itself is moving from A to P. Therefore, AP will represent, and AP is the displacement. AP is the displacement or AP represents the displacement. There is a difference. But in this particular case, when the tip undergoes the displacement from A to P, AP is the displacement S1 and AP also represents the displacement S1 because AP is an arrow. So we are getting in this way 3 arrows. When you add 3 arrows vectorially, so we are getting 0. This is mathematics. But what does it mean physically? This is a physical experiment of moving from A to P along the straight line, from P to B along the straight line, and B to A, back to A along the straight line. You are getting the same initial position, the final position, initial position, both are same. In this way, if you move from A to P, P to B, B to A, we are getting the initial position. You will be coming back to your original position. Therefore, the net displacement must be equal to 0. Therefore, we can say that 0 vector in the case of displacement, if physical signifies that you get back to your original position. In this case, the 0 vector in this case S equal to 0 physically signifies that the net or the resultant displacement is 0. So what does it mean physically? This means that the tip, this tip comes back to its initial position A. This is the physical significance of 0 vector, one of the example. Physical significance of 0 vector. This is one example, of course. I can give you many examples like F1 plus F2 plus F3. 3 forces, when you add, you will get 0 force, no net force. Many examples you can give. Example of physical significance of 0 vectors. After triangle of vectors, let us talk about the parallelogram law of vectors. How to convert a triangle to a parallelogram? This is a vector triangle formed by the displacement of the tip of our pen from A to P and from P to B and from A to B. So we are getting 3 vectors S1, S2 and S. This is the resultant. S is equal to S1 plus S2. S is equal to S1 plus S2 by triangle law of vector addition. What we have discussed just now. Well, let us now reverse the order of displacement. You have displaced your tape from A to P, then P to B by S1 and S2 respectively. Let us now do the same thing. What is that same thing? To get this point P in different way. Only one option is available. What is that option? We have to undergo a displacement S2 first. So this is the displacement S2. From A, you are undergoing the displacement S2. You have to draw a line parallel to S2. That means it has to go. Really it is moving. It is undergoing the displacement. Really. It is not just a geometrical diagram. It is the actual displacement from A to say point Q. This vector AQ is equal to the vector S2 because you are undergoing the displacement S2 exactly. So when you are translating this vector in this way without changing its angle of orientation, then you are getting the same vector. That means you have to undergo the same length in the same direction as that of S2 in this way. Then you have to undergo another displacement, that is S1 from Q, and you will get the desired position B. From Q to V you have to travel, or you have to undergo displacement S2. You have to undergo displacement S1, and you can find that finally you will get the same position, same destination B. So there are two different paths. The path A, P, B, and A, Q, B. So you can write what we have done, we have to just write that by reversing the order of displacement. First S1, first S2, and then S1. The TAFE can get the final position. What is that final position? Point B via Q, via the point Q, undergoing two displacements S2 and S1, S2 first, then S1. In this part, first S1, then S2. Therefore, I have told you that by reversing the order of displacement, so we have two paths. The paths are AP, B, and AQB respectively. So by reversing the order of displacements, first S2, then S1, obviously you will get the same point because S1 is equal to this S1 because these two are parallel. S1 means AP is exactly equal to QB, same direction and same magnitude. And PB will be exactly equal to AQ, same direction and same magnitude. So anybody can understand that this is a parallelogram. This is a parallelogram. So we can write that as a result, we obtain a parallelogram. Parallelogram what is a parallelogram? छोड़ा तो रिपीट करिए
कोई टेक के रिपीट करिए तो मैं वॉइस में काट देवे थी पार्ट पूरी पैरेललोग्राम तो मैं उससे वॉइस को वन टेक में काटी भी नहीं
हां ठीक है
तो वन सेकंड टेकिंग
parallelogram A, P, B, Q. These vectors S1 and S2 in this way and S2 and S1 in this way, we will get a parallelogram. And in this parallelogram, we can say that these two sides, AP and AQ, are adjacent sides. AQ and QB are adjacent sides. QB and BP are adjacent sides. And BP and PA are adjacent sides. AP and PB are adjacent sides. AQ and QB are adjacent sides. But for the sake of simplicity, let us choose AP and AQ. These two are adjacent sides of this parallelogram. The adjacent sides AP and AQ represent the vectors S1 and S2 respectively. Then the diagonal, what is the diagonal? AB, which passes through the common tails. This is the tail of vector S2, this is the tail of vector S1. This is the common tail, or the starting point, or the common tail of these two vectors will represent the resultant of S1 and S2. S is equal to S1 and S2. So S is the resultant, and this resultant is given by the diagonal AB. This is diagonal and S1 and S2 are the adjacent sides. S1 is represented by the side AP and S2 is represented by the side AQ. AP and AQ are they adjacent sides of the parallelogram. If the adjacent sides of the parallelogram represent these two vectors S1 and S2, the diagonal AB, that is the resultant of these two vectors. So we can write the statement as a statement of parallelogram law of vectors. So the triangle law of vectors can be used to demonstrate that yes, we can get a parallelogram by using two such triangles. So we will get parallelogram. Law of vector addition, which states that if the adjacent sides of a parallelogram, this is a geometrical symbol of a parallelogram. If the adjacent sides of a parallelogram represent any two vectors S1 and S2, then the diagonal, which diagonal? that passes through the tails of these two vectors. These are the tails of these two vectors, common tail, because these tails they meet at this point A. The diagonal which passes through the tails of these vectors S1 and S2 will represent the resultant of these vectors. The resultant of these vectors. So we can write the resultant is S, or we can write the diagonal AB vector is equal to the adjacent sides represented by the vector AP and the vector AQ. AB is the net displacement or resulting displacement. AP is the displacement S1 and AQ is the displacement S2. So it looks like the expression of triangle of vectors, but actually there is no such difference, because by these two triangles we are getting a parallelogram. So this is the parallelogram law of vector addition. This is one of the basic law for vector addition. Without a proper understanding of the parallelogram law of vector, a triangle law of vector, we cannot proceed further. So if you can understand this, I think the entire physics will be enjoyable for you. Let us calculate the length of the resultant and the direction of the resultant with respect to S1 or with respect to S2. Let us assume that the angle between these two vectors be theta. S1 and S2, the angle between S and S2 be theta let. Then the resultant S is equal to S1 plus S2 has the magnitude S is equal to S1 square plus S2 square
क्रॉस कैंसिल कीजिए टेंशन न चलो
S is equal to S1 square plus S2 square plus 2S1 S2, the cosine of the angle between these two vectors, the square root of the whole quantity. This is the magnitude of the resultant. And direction, the direction of any vector can be given by an angle. Let the resultant act at an angle phi with respect to the vector S1. If this is so, then the magnitude the direction of can be given as phi equal to tan inverse S2 sin theta by S1 plus S2 cos theta. So these are the expressions for the magnitude and the direction. This is the magnitude of the resultant, and this formula gives us the direction of the resultant. Well, this is simply based upon Euclidean geometry. Let us try to prove it. Let's now prove that S equals square root of S1 square plus S2 square plus 2S1 S2 cos theta. This is the magnitude of the resulting displacement or resulting factor, and its direction with respect to S1 is phi is equal to tan inverse S2 sin theta by S1 plus S2 cos theta. We can use Euclidean geometry and some trigonometry also. For this we need to have a construction. What is the construction? We have to extend the AP in this direction, and if you drop a perpendicular to the projection or the extension of AP from B, let this perpendicular meet this extended line at point say M. Let me repeat. The construction is very simple. What is that? Let us produce AP and drop a perpendicular to this extended line from B. For that perpendicular, BM. So we are getting a triangle BBM. In this triangle, this is a right angle triangle. In this right angle triangle, PBM, this angle is equal to theta because these two sides are parallel. When these two sides are parallel, this angle will be exactly equal to this angle. So in this right angle triangle, PM is equal to PV cos theta. As you know, that in any right angle triangle, let it be PMB. This is if this is the angle theta, this is the base, this is the height, and the perpendicular phi, this is hypotenuse H. The simple trigonometry. The property of triangles says that V by H, base by hypotenuse, is equal to cos theta, and the perpendicular upon the base or perpendicular upon the hypotenuse is equal to sin theta. Then B is equal to H cos theta and P is equal to H sin theta. In this case, the base is PM, the hypotenuse is PB. The perpendicular is BM and hypotenuse is PB. Well, but the PM is equal to PB. What is PB? This is exactly equal to S2. So its magnitude is S2. That's equal to PB. So PM is equal to PB cos theta, but PB is equal to S2. So S2 cos theta is equal to PM. And BM is equal to PB means S2 sin theta. So we can write this is S1, this is, what is PM? S2 cos theta. What is VM? S2 sin theta. So in which triangle? In this triangle, A, B and M. In the right angle triangle ABM, the hypotenuse H, that is AB, is equal to square root of AM square. This is the base for this right angle triangle, this is the height. So AM square plus MB square. M square plus MB square. But what is AB? AB is nothing but magnitude of the resultant height. And M, what is M? M is equal to S1 plus S2 cos theta. S1 plus S2 cos theta. Magnitude of S1 plus S2 cos theta. And what is MB? MB is equal to S2 sin theta. I repeat, M is equal to AP plus PM. But what is PM? S2 cos theta. This is S2 cos theta, this is S1. So this length is S1 plus S2 cos theta. M is equal to S1 plus S2 cos theta, and MB is equal to MB or BM is equal to S2 sin theta. So put MB equal to S2 sin theta square of this. So it is very simple to write. S1 square A plus B whole square equal to A square plus B square. 2AB, S1 S2 cos theta, and this is S2 square sin square theta. And you know S2 square sin square theta plus S2 square cos square theta is equal to S2 square because sin square theta plus cos square theta is equal to 1. So in next step you will get the answer. S is equal to S1 square plus S2 square cos square theta plus S2 square sin square theta, that is S2 square. Then rest of the factor is 2S1 S2 cos theta. So this is the first proof of the magnitude of the resultant. Let us now prove the direction of the resultant. Let's now try to prove the equation number 2. In equation 1, we have mentioned the magnitude of the resultant. You can note here that this diagram is known as vector triangle. Two vector triangles means there is a parallelogram. This is the vector triangle. This one this is a triangle ABM, and this is the triangle PMB. So I made it the scalar triangle in this way. This is the vector triangle, this is the scalar triangle. This is S2 cos theta, and this is S1. So this is S1. This is S1, this is S2 cos theta, therefore this is S1 plus S2 cos theta, and this is S2 sin theta. And in this triangle, we have to start from the triangle PMB. In the triangle, right angle triangle PMB, in this triangle PMB, tan phi. Tan phi is equal to, in this triangle, this is the hypotenuse, sorry, this is the perpendicular P, and this is the base. Tan phi is equal to perpendicular upon base. For the perpendicular, this is S2 sin theta. For the base, S1 plus S2 cos theta. Next step you are getting phi is equal to tan inverse S2 sin theta upon S1 plus S2 cos theta. Hence proved. The equation number 2. So let us see the key steps to prove equation 1. Take which triangle? Take this triangle ABM, right sided triangle ABM, to prove equation 1, which gives the magnitude of the resultant. And to find the direction of the resultant, at what direction the resultant points with respect to S1 or S2, we have taken with respect to S1, let it make an angle phi. So phi is equal to tan inverse S2 sin theta by S1 plus S2 cos theta. For this to prove, the key step is, for equation 2, take which triangle? The green shaded triangle, this one, PMB. So take the triangle PMB, and in that triangle, tan theta is equal to perpendicular upon base, that is the S2 sin theta upon S1 plus S2 cos theta. This is not tan theta, that is the tan phi. This is phi, this is not theta. Tan phi. So what we need? We need the direction and we need the magnitude of the resultant vector. So that's not very difficult. If you know 8th standard geometry and trigonometry, Euclidean geometry and trigonometry, you can prove it very easily. My dear physics friends, this time we will talk about the polygon law of vector addition. This is a generalized law of vector addition. Triangle is a polygon of 3 sides. Quadrilateral is a polygon of 4 sides. Rectangle and a square are the polygons of 4 sides. Pentagon is a polygon of 5 sides. Hexagon is a polygon of 6 sides, and so on. In general, let us take a polygon of n sides. Let us choose either clockwise or anti-clockwise. This is clockwise, this is anti-clockwise. I have chosen the anti-clockwise manner. These sides, you leave this side, you leave this side. This is a closing side. These are the n-1 sides. First side, second, third, and so on is n-1 side. The sides represent the vectors a1, a2, a3, a, n-1 respectively. In which order? In anti-clockwise order, or in one sense, anti-clockwise sense. So the sides of a polygon represent the vectors in a particular sense. If there are n-1 vectors, a1, a2, a3 up to a n-1, represented by the sides of a polygon of n sides. It is up to n-1 side, n-1 sides plus this another last side. If you add n-1 plus 1, we are getting n sides. A polygon of n sides taken in one sense or one order. The sense we have chosen, anti-clockwise sense. Anti-clockwise sense or anti-clockwise order. Taken in one sense, the closing side, this is the closing side, taken in the reverse order. With anti-clockwise sense, we are taking the closing side in clockwise sense. And this closing side, taken in the reverse order, must represent the resultant of these vectors a1, a2, a3 up to an-1. So the vector sum of all these vectors up to an-1 from 1 is equal to the resultant R. This is the vector addition or the summation or the resultant or the net effect of all these vectors is equal to R. So this is the mathematical statement. So we can write mathematically we can write in this way. And the proof is very simple. Let us take the closing side as a vector, but in anti-clockwise sense, let it be n. So all the sides taken in a single order. When we are, suppose let us take this vector as displacement. When you move in this way, undergoing n displacements, S1, S2, S3, S4 up to Sn. So you are coming back to the original position. So the net displacement is equal to how much? A1 plus A2 up to N. The net displacement or net effect of all these vectors represented by the sides of the polygon taken in a particular order is equal to the resultant. That's not that resultant. It is equal to 0. It's equal to 0. This is the closing side. This is the 0. This you know already. Now, we have to bring n, that is n minus 1 plus n. A1 plus A2 in this way up to n minus 1 must be equal to minus n vector. But n vector and r vector are opposite. Since n is equal to minus r or r is equal to minus n, these are equal in magnitude. These two vectors are equal in magnitude but oppositely directed. Therefore, they are negative vectors. So putting minus n as r vector, we have proved that yes, r is equal to the sum of all these vectors ranges from first vector a1 to n minus 1th vector, addition of all these vectors or summation of all these vectors or vector sum of all these vectors from 1 to n minus 1 is the resultant or net effect. This is proved. So this is the statement of polynomial law of Hecker's, which states that if the sides of n minus 1 sides of a polygon of n sides represent n minus 1 vectors taken in one set. Hi kids, I have prepared some videos on vector addition very scrupulously. Have you gone through that?
Yeah, we have gone through a few of them. The first video was interesting and the others were okay. I think we need to explain it in more interesting way.
How will that be possible?
Yes, we have an idea. We have come with a bunch of practical funny questions. If you use them, I'm sure that people will grasp better.
Well, so what are your questions? Can you give me your first question?
What is displacement? Why is displacement a vector? And why distance is a scalar?
Oh well, is there any other question?
Yeah.
Please tell me.
How can displacement be 0 even when distance is not 0?
Well, it's interesting. Okay kids, do you have any other funny questions?
Sir, we have another doubt regarding vector addition. We know that 2 potatoes plus 3 onions equal to 5 potatoes plus onions. What will happen if we add 2 Newton of force plus 3 meter of displacement?
Well, it's interesting. Yeah, of course I am very happy that you are asking very interesting questions. I hope you have come with some other questions.
Yes, sir. Sir, in your previous video, you have talked about triangle law of addition.
Yeah.
Now, if I have a triangle and 3 vectors are passing in a triangle, like from A to B, B to C, and C to A, what is the resultant? Is it 0?
Oh, it's a very funny questions. Well, my dear kids, let me try to answer these questions you have posed. These questions are very interesting, especially very fundamental questions, even though I have discussed some of these questions in my last videos. Let me recapitulate all this. The first question is about the character of distance and displacement. Distance and displacement. Even though these two things will be discussed in the chapter of kinematics, but without referring to distance and displacement, we cannot start the vector and the vector addition, because for vector addition, the displacement vector is the fundamental entity. It's a fundamental factor to start vector operation, the subtraction, the addition and subtraction of vectors. Displacement is a vector quantity, but distance is a scalar quantity. By distance of 5 meters means is no direction. By the displacement of 5 meters towards east, this is the displacement. We can write 5 is the magnitude and towards east is the I cap direction. This is east, this is west, this is north, and this is south. So each direction is given by the unit vector I cap. 5 meters towards east is different from just 5 meter distance. So distance of 5 meters is no direction part is there. It may be the straight distance from here to here, A to B. It may be in a curve. The curve distance is the straight distance. So this is the length of the path. The distance is the length. Distance is length of the path. But displacement is different. But displacement from suppose A to B is the starting point, or you can say initial point, and B is the final point or destination. You are moving from A to B. In many paths you can do that. In many paths you can move from A to B. Countless paths, innumerable paths you can move from A to B. Path 1 to n number of paths, countless paths. However, your result is same. What is the result? To get the point, final point B from A to B. So the straight line distance, so the shortest distance between the initial and final position, initial and final point, and given an arrow towards the final point. This is correct, but this is wrong. This is correct. The arrow should be given at the end of the segment. Then this is the correct geometrical or graphical representation of the displacement. But if you put the arrow in the mid, it's the wrong representation. So this is the displacement. It is, we can say in different way, that when you observe the point B, the final point from the initial point, This is the position vector of the final position with respect to the initial position. So displacement is nothing but position of the destination or the final position with respect to the initial position. And since, as I explained in my first video, if you ask a baby, where is the point B? When the baby is standing at the point A, the baby will point his finger towards B. So the position of the B with respect to A can be explained by pointing the finger. Therefore, the vector AB, or the position of B with respect to A, is a vector quantity. That is what is numerically equal to the displacement. So displacement is the first fundamental vector quantity. After position vector, of course, displacement is nothing but the position vector of the final position with respect to initial position. So basically the question was between displacement and distance. Displacement is a vector quantity, whereas distance is a scalar quantity. Displacement has direction and distance has no direction. Between any two points, there can be many distances. There can be many distances. These are all different lengths. Length 1, length 2. There can be many distances. But the displacement is one. It is pointing from the initial position to the final position and directed in this way. And if you put the tip at the end of the segment, really the point, the tip of the marker moves from A to B in different paths. However, even though it may not move in this way, but always the straight line between A and B, the straight line segment AB, having an arrow at the point B in this way, represents this vector quantity. Let's talk about the second question. The second question is, why should a distance not be 0 in general, whereas a displacement of a moving object can be 0. Why can a distance not be 0, whereas the displacement of a moving object be 0? This is the question, second question. For this, let me take a simple example. There are 2 points, point A and point B, starting point, ending point. You can move in many different paths. You can move in this way. You can move in this way. You can move in this way. Path 1, path 2, path 3. These are the distances. When you are moving between 2 points, the length of the paths cannot be 0. It is quite clear, you can see this. When the tip moves from A to B, the lengths cannot be 0. L1 is not equal to L2, is not equal to L3. In general, is not equal to 0. How we can say this? However, the distances means the length of the path covered cannot be 0, whereas the shortest path can be 0. How? If you imagine the initial point and the final point, initial position and the final position at the same place, then you can move in this way, you can move in this way. The length cannot be 0. However, the shortest distance between these 2 points, when these 2 points coincide, can be 0. And the shortest distance is nothing but displacement. The shortest distance between these 2 points is nothing but displacement. We can say the displacement in this case is nothing but AB. Can be 0, can be 0. It's a 0 vector, it's not simple 0. It's not a 0 scalar, it's a 0 vector. When A coincides with B, the initial and final positions, the starting point and the destination, they coincide. I mean, the point, moving point, or the object or the particle comes back to its original position. In that case, the displacement can be 0. However, distance can never be 0 for a moving object. Now this, I think this answers your question. Interestingly, the third question you have posed regarding the addition of scalars and vectors, the basic question. You have taken 2 potatoes and 3 onions, you are adding, mixing it up, they don't lose their identities, and you are getting the total number of particles is 5, and it is a mixture of onions and potatoes. So the scalars you can add in this way. 2 liters of milk and 3 liters of water, when you add, you are getting 5 liters of the mixture of milk and water. It is totally practical. Day-to-day life we experience these 2 examples. So 2 plus 3 is equal to 5. 2 of x, 3 of y is equal to 5 of x plus y. 5 of x plus y means the mixture of x and y. It means like that. X plus y I wrote in that sense. But 2x plus 3y is not equal to 5 into x plus y. It doesn't make any sense in that way. 2 articles or 2 numbers of x quantity plus 3 numbers of y quantity is equal to 5 numbers of the mixture of x and y. It means that. Whereas to measure displacement plus 3 Newton force, suppose. If you add these 2 vectors, it is a vector, suppose A, this is a vector B. If you add it, what does it mean? This is the question you have posed. And the straight answer is that you cannot add 2 vectors of different varieties. You cannot add the displacement with force, force with velocity, displacement with velocity. 2 different types of vectors you cannot add. So in that way, A vector plus B vector, when these 2 vectors are not, they don't belong to a particular quality of vector or particular types of vector, when you add them or subtract them, it doesn't make any sense. So A plus B is meaningless. Is meaningless. This is the answer. So from your third question, we have understood that different types of vectors such as force plus velocity plus displacement, it doesn't make any sense. So similar type of vectors can be added. Force can be added with force. Displacement can be added with another displacement, and the velocity can be added with another velocity vector. Based upon this concept of addition of similar type of vectors, you have put the fourth question, that in the triangle law, suppose you take a triangle ABC, ABC, and you have stated that one vector, suppose this is a force vector, the force vector F1 is pointing along AB from A to B, another force vector, say F2 vector, is pointing from B to C, and the third vector F3 vector, it points along C from C to A in this way. If these vectors, if three vectors, needless to mention, similar type of vector means force vector or velocity vector or displacement vector, if three vectors F1, F2 and F3 point from A to B, from B to C and C to A. In the triangle ABC, the fourth question you have posed, then can the addition of these three vectors be zero? This is the question. Well, if you think that the triangle law statement, in the first glance many students may tend to write 0, but it is not 0, is the wrong answer. So the answer is no. It's very strange. Why is this so? To explain this, we have to go to the basic statement of the triangle law of vectors, which states that when these vectors F1, F2 and F3 are represented by the sides of a triangle, if the vectors are represented by the sides of a triangle, then in cyclic way, of course in cyclic way, then f1 plus f2 plus f3 will be equal to 0. But here these vectors point from A to B, B to C, C to A. They are just passing through the sides AB, BC and CA, but they are not represented by the sides. Now a question arises. When this statement is correct and this is wrong, what is the basic difference? The basic difference is, here in this case we have asked the sides of the triangle do not represent the vectors f1, f2 and f3. They are just passing through the sides. Then in this case f1 plus f2 plus f3 cannot be equal to a 0 vector. Now we may ask question, how can a triangle represent these forces? If you take the triangle A, B and C, if you ask that these forces not only point from A to B, B to C and C to A, but also the sides represent the forces, then the diagram would be in this way. This is the force F1. The tip should be in this way. Its tip of the arrow cannot be in between, because the side AB represents the force F1. That means the tip will be here. Tip will be at B, and the tip of the vector F2 will be at the point C, and tip of the vector F3 will be at the point A. In this case, the sum of these three vectors will be equal to 0. It may be force, it may be velocity, it may be displacement, but displacement thing will be different. When you say displacement, then A to B, B to C, C to A. Displacement, if you take, instead of force, if you take a specific example of the vector as displacement, then you can write AB plus BC plus CA, because these are displacement. S1 plus S2 plus S3 is equal to 0. It's correct. Always this is 0. But the displacements are nothing but the sides. But for any other vectors, in general, if you put the question in this way, that F1, F2 and F3, they just point along the sides of a triangle, but they are not represented by the sides of the triangle. Then some of these three vectors, when they are pointing or they are passing through the sides in cyclic way, some of these three vectors may not be equal to 0. But in this case, the vectors are represented by the sides of a triangle. Specifically, if you ask this question, then it will satisfy the statement of the triangle of vectors. According to that, the sum of these three vectors will be equal to 0. I hope this answers your question.